I'm going to introduce the electric field based entirely on Coulomb's law, which you saw last time, but recasting it in a slightly different language. So let me suppose that right here I have some nice, big, hefty, charged object with a charge that I'm going to call QS. S stands for source. And I'm going to recast Coulomb's law with a new language in which I'm going to say that any source of charge here creates around it an electric field. So in particular, I could pick any point, and I'll pick this point. This is any random point. We'll call it the point P. And I can ask, what is the electric field, which we're going to always refer to by a vector capital E? What is the electric field at the point P caused by the source of charge QS? So what is the electric field right here? I have charge there, it's making an electric field here. It's making an electric field there, it's making an electric field there, it's making an electric field there. But right now I'm asking about this spot here. So I need to define what I mean by the electric field at the point P, and here's how we do it. I say, well, in reality there's no charge at P. All there is an electric field. But for me to define the electric field, the way I define it is I say, suppose that in my mind I imagine there is a tiny little bit of charge there, which I'm going to call QT. T stands for test. Suppose that I have a test charge here. What's the force on this test charge? Well, we know that from Coulomb's law, the force on this test charge is a vector that points in this direction. And the definition of the electric field is the electric field at the point P caused by the source of charge QS is given by that force on the test charge caused by the interaction between the test and the source charge. This is the force on a test charge QT at the point P divided by QT. That's the definition of the electric field at the point P caused by the source of charge QS. Now, let's think about this. And in particular, let's ask ourselves, what's the direction of the electric field at the point P? Now, if QT is positive, well, I have the force. We decided that if QT was positive, the force was pointing that way. And I divide by a positive quantity. And so the electric field at the point P caused by the source of charge QS is in a vector pointing in this direction. The electric field vector points in the same direction as the force if QT is positive. So I just turned this white arrow into my way of representing the electric field at the point P. But what about if QT were negative? Well, if QT were negative, then the force would point this way. But then the electric field would be, I would take the force and divide by QT, and QT is negative. So when I divide by a negative quantity, that flips the direction around. And so the electric field points in this direction, no matter whether QT is positive or negative. And this gives us a hint that this electric field, well, we've just seen that it doesn't depend on the sign of the test charge, but in fact, it doesn't depend on the magnitude of the test charge either, as I'll now show you. Let's just use Coulomb's law. So let me rewrite the electric field caused by the source S at the point P. Let's rewrite that using Coulomb's law. So Coulomb's law tells me that this FST is given by a fundamental constant K times QS QT times a vector, a unit vector, pointing in this direction, and that this unit vector is the unit vector pointing from S towards T, divided by the distance between the source charge and the point P squared, so that this distance here I will call RST, and I divide by RST squared. So that's Coulomb's law telling me what this force is, but now I have to divide by qt, and I'm going to divide by qt by erasing it. So I divide by qt, the qt is gone. And now we see that the electric field caused by the source of charge qs at the point P, what does it depend on? Well, it depends on how strong the source is. It depends on qs. There's qs right there. So how strong the field is at this point P depends on how much charge you have over there. It's this charge that's making the field. It also depends on which point P you picked. If I had picked the point P over here that's much closer to the source of charge, then this r squared downstairs would be smaller, the electric field would be bigger. So the electric field caused by the source of charge is bigger close to the charge, it's smaller farther away. It also depends on the location of P because the direction of the electric field depends on this unit vector. And if I'd picked a point P over here, this unit vector would point this way. So this electric field depends on how much charge you have at the source, and it depends on where you are. But it does not depend on that test charge that I introduced as I defined it. So the way you should think about this now, this is a recasting of Coulomb's law. The way you should think about this now is, here I have a charge, qs. This qs makes an electric field. It makes an electric field at all points. The electric field that it makes at this particular point is given by Es of P. Here's my expression. And what good is an electric field? What does an electric field tell me? If I were to stick a charge q down at the point P, then that charge qt would feel a force. It would feel a force Fst P. So I'm sticking a test charge down qt at the point P, and I ask, what is the force on that charge? Well, by very simply rearranging this equation, that is given by qt times the electric field at the point P caused by the source. So this second equation, which is a trivial rewrite, on the one hand, a trivial rewrite of the definition. On the other hand, this will become the way you think. The way you will think now, instead of starting with Coulomb's law as being about forces between two charges, you will separate that out into two steps. I have some charge. Here it is, qs. This qs makes an electric field. What's the field that it makes? Well, that's this equation. My source charge qs makes an electric field with this particular form. And when I look in this equation, nowhere in here is there any other charge except for qs. Yes, there's a point P, but there's no charge yet at the point P. This field is at P even if there wasn't a charge there. But what good is an electric field? What does it do? Well, what an electric field does is it pushes charges around. So you see we've separated out Coulomb's law into two parts. The first charge, qs, makes an electric field. And then that electric field pushes around other charges. If I stick down a test charge here, it feels a force. It's pushed around by the electric field, and it's pushed around according to this equation here. And these two together reproduce Coulomb's law as we saw it last time. But what we will see going forward is that this is actually a much more powerful way of thinking about electric forces, and that this electric field, at this point, you're probably scratching your head and wondering, why am I spending so much time introducing this? What you will see as we go forward is that this electric field, which is introduced in such a simple and straightforward way, is going to take on a life of its own.